deBroghlie came up with this cool theory that anything with momentum, which is momentum's a particle type property, anything with momentum has an associated wavelength. Wavelength obviously being a very wave-like property. His equation is relatively simple. The associated, or the deBroghlie wavelength, is Planck's constant divided by the momentum. Planck's constant is like other constants in physics. It's just a number in this case it's a crazy small number, but it's just a number that relates that Planck came up with when he did Planck's law, when he did the energy of light and sort of kick-started the whole quantum thing. For this particular one that I made up, to make it similar to what we've done with electrons, instead of giving you the speed of the baseball, instead of giving you the speed of this larger object, I've given you the energy. So our first step will be to deal with that energy. A baseball, if it's moving with some kinetic energy, we know that kinetic energy is always 1/2 mv squared. We're going to use that to find the speed, and then we can plug the speed into the deBroghlie equation to get the actual wavelength. So for the numbers I cooked up, 175 joules of energy is 1/2. The mass of a baseball is 140 grams. We can use that to find the speed. After flip-flopping things around and square rooting, this one is nice. We get a speed of 50 meters per second. That's pretty fast for a baseball. That's like 110 miles an hour. So if you were to Google like Major League Baseball pitchers and how fast they pitch, that's going to be a really fast fastball. If we can run with that number though, now that we've got the speed, the deBroghlie wavelength is just the constant divided by momentum. The constant is always the 6.626 number. For the numbers I made up this time, the mass of a baseball, you can Google it, but 140 is close to a regular baseball within a gram or two, and the speed that we worked out to was 50. If you do the math on this and crunch it out, you are going to get a ridiculously small number. 9.5 times 10 to the negative 35. We could round it off to 1 times 10 to the negative 34. However you round it off, however you deal it, it is ridiculously small. Compared to the size of the baseball, this number is approximately 0. What that means is we're not going to see any quantum effects of fast-moving baseballs. The deBroghlie wavelength is basically 0. Without a wavelength, we're not going to see any cool interference or anything else happening with a baseball or anything that large. However, if we cooked up more realistic numbers for, say, an electron or a proton, the deBroghlie wavelength is not almost 0, is noticeable, so you do see some noticeable quantum effects with those other particles.